In the name of Almighty God, I'm Master Sankoshi, and today I want to talk about magnetic dipole coupling for nuclear fusion. For magnetic dipole coupling, the indirect coupling strength between a deuterium and helium-4 donor transition assumed to start out in the excited states, for example, as deuterium and a deuterium helium-4. Receiver transitions assumed to start out in the ground states, for example, as helium-4. Per the nuclear excitation transfer model discussed in the section 5.1 and 5.2 is as U magnetic to the power of 2 is equal to phi deuterium absolute micro phi helium 4 multiplied by zeta oscillator absolute BB and zeta oscillator multiplied by zeta deuterium absolute micro and zeta helium 4. Rosetta oscillator describes the state of the spine which gives rise to the magnetic field at the sides of the deuterium donor systems and the helium-4 receiver systems. See the section 6.13 for the derivation of the term, which yields as a U magnetic to the power of 2 is equal to 10 multiplied by square root U nuclear divided by U molar multiplied by e to the power of minus g to the power of 2 micro n b to the power of 2, where micronuclear divided by V molar is the ratio of the characteristics nuclear to the molecular volume as discussed on section 6.3. Note that magnetic decoupling affects the deuterium state of the nuclear wave function for deuterium based on the reference 91. Recall that the minimum rate starting rate in equation 78 time minimum is equal to 2 divided by h multiplied by 2 absolute 1 minus n multiplied by Vhn to the power of 2 divided by delta mc to the power of the square root n deuterium and n helium 4 plugged in the U magnetic to the power of 2 for Vgen to the power of 2 yields the tau minimum is equal to 2 divided by h multiplied by 2 multiplied by absolute 1 minus m multiplied by 10 multiplied by square root U nuclear divided by U molar multiplied by e to the power of minus g to the power of 2 micro n b to the power of 2 divided by delta mc to the power of the square root n addition to n helium 4. To evaluate these expressions, we need to consider the values of the all relevant parameters. We take absolute 1 minus n is equal to 0.1. Nu nuclear divided by nu molar is equal to 6.64 multiplied by 10 to the power of minus 12 when G is 94.8, where the volume ratio and the gamma factor are for the deuterium 5 state and where absolute 1 minus n is for the deuterium divided by 3 plus 1 divided by helium 4 contribution to the deuterium helium 4 transitions per section 6.5, the volume ratio and the on-screen gamma factor G take on the values determined in the section 6.3 and are discussed in more detail here. Moreover, we follow the scenario given in the introduction, which energy deuterium divided by neutron is equal to 0.001 multiplied by 0.3 multiplied by 1 divided by 25 and helium 4 divided by n is equal to 0.01, where we assume a loaded lattice where every 1000 unit cell contains a deuterium molecule and where 30% of the deuterium molecules are in the 5 deuterium state. See figure 38 in section 6.1 with only one of the 25 possible deuterium 5 states which J is equal to 1 being involved in the minus micro multiplied by B transitions for a Z-directed magnetic field and where every 100 unit cell contains a helium 4 nucleus. The nuclear magneton has a value of micro n is equal to 3.15 multiplied by 10 to the power of minus 8. If V divided by temperature, and we assume magnetic field strength of the B is equal to zero point 0.1 Tesla. Note that this model would be most relevant under conditions where the nuclei that undergo transitions are in the vicinity of a strong magnet such that the interaction of the nuclei with any individual electronic spin is idealized to be uniform. Plugged in all of the above values results in a minimum transfer rate on a screen of time minimum on a screen is equal to 2.64 multiplied by 10 to the power of minus 89 multiplied by s to the power of minus 1. Since we use the unscrewed gamma factor g above, we can consider the effect of a screening by multiplying with this e to the power of 2 delta gamma screen, where delta gamma screen is equal to 47.8, accounts for electron screening of the deuterium 5 channel of the deuterium nuclear wave function with the 350 electron volt screening potential. See section 6.3. The screening factor per section 6.3 comes in twice here, since screening affects the donor side transitions as well as the receiver side transitions. This results in tau minimum on screen is equal to 8.73 multiplied by 10 to the power minus 48 1 per second. To obtain the maximum rate peak rate of the decay enhancement pulse, we apply the additional decay enhancement per sections. 5.2 tau maximum is equal to tau minimum 1 divided by 4 n deuterium deuterium. For n deuterium deuterium is equal to 10 to the power of 15. This yields tau maximum screen is equal to 2.18 multiplied by 10 to the power of minus 33 1 per second. Again, this is the population level transfer rate. For example, the rate at which excitation from the ensemble in group A transfers to the ensemble in group B to obtain a rate per neutron pair that is comparable to the estimate given by the Konin and Nauberg in 1989. In reference 20, we normalize the expression. Applying this normalization to decay enhanced expressions, we obtain, for example, tau maximum screen divided by energy from deuterium is equal to 2.18 multiplied by 10 to the power of minus 48 1 per second, and the tau minimum screen divided by energy from deuterium is equal to 8.73 multiplied by 10 to the power of minus 63 1 per second. Note that this rate is not the observable range. See the equation 2.1. Also note that the same amount of screening 350 electron volt applied to the base rate given by the Koenig and Neuenberg 1989 in the reference 20 and reproduced in section 6.3. See table 8 yields a rate per deuteron pair under the order of the 10 to the power of minus 20 1 per second. Therefore, including the deuteron tends to helium-4 transition to nuclear excitation transfer based on magnetic coupling is an interesting scenario to study, but it doesn't appear to outcompete the spontaneous fusion rate. Now I want to go through the electric dipole coupling. And next, we consider a situation that corresponds to the system discussed in 5.2, where electric dipole coupling results from oscillations of the nuclear photons and plasmons. For electric dipole coupling, the indirect coupling strength between a deuterium helium-4 donor transition assumed to start out in the excited state, for example, as deuterium and a deuterium helium-4 receiver transition assumed to start out in the ground state, for example, as helium-4 is a U electric to the power of 2 is equal to phi deuterium absolute D phi helium-4 multiplied by E helium-4 multiplied by E helium-4 oscillation multiplied by phi deuterium absolute D helium-4. See section 6.14 for derivation of the terms which yields here given for acoustic phonos. U electric to the power of 2 is equal to T divided by 4 alpha multiplied by H at gamma radians divided by delta MC to the power of 2 multiplied by H omega R to the power of 2 divided by delta MSC to the power of 2 to the power of 2 multiplied by square root MAD to the power of deuterium Ma helium 4 C to the power of 2 divided by neutron Z to the power of 2 multiplied by PADC equation tau R, where gamma radian is a radiative deuterium-deuterium fusion rate of the photon emitting channel, which is given in reference 92, and shown below. The fine structure constant is given by the alpha, and tau R is the acoustic photon mode lifetime as a function of the frequency of the mode. FR variables specific to this coupling are defined as follows: 92 alpha is equal to electron to the power of 2 divided by 4p epsilon 0 hc. Gamma radiative is equal to 6 multiplied by 10 to the power of minus 8 gamma deuterium tau R is equal to 10 to the power of minus 12, then we multiply by 10 to the power of minus 7. FR divided by 1 megahertz to the power of minus 3 divided by 2 seconds, where gamma deuterium is the rate formula in terms of the on-screen deuterium rate given by the Konya and Nuremberg 1989 in reference 20. Recall the minimum rate, starting rate in equation 78. Tau minimum is equal to 2 divided by h multiplied by 2 absolute 1 minus n multiplied by v to the power of 2 divided by delta msc to the power of the square root and a deuterium and a helium 4. Plugging in the U electric to the power of 2 for V gen to the power of 2 yields tau minimum is equal to absolute 1 minus n multiplied by 3 divided by alpha z to the power of 2 multiplied by h omega r to the power of 2 divided by delta msc to the power of 2 all to the power of 2 again multiplied by square root m deuterium m helium for c to the power of 2 divided by delta mc to the power of 2 multiplied by p dissipation tau r divided by delta mc to the power of 2 gamma radiative divided by gamma uh, deuterium multiplied by gamma deuterium square root and deuterium and helium 4 divided by n. Here we take advantage of narrowing the ratio of gamma radian to gamma deuterium, so we can express this rate formula in terms of the on-screen deuterium rate, which allows for easy comparison. Gamma deuterium is given as section 6.3. Gamma deuterium is equal to 3 multiplied by 10 to the power of minus 64 1 per second. The above on-screen rate gamma deuterium is consistent with the use of the gamma factor of gamma is equal to 90.4, which is appropriate for the P3 states considered for electric dipole coupling. See section 6.3. To evaluate T minimum, we need to consider all the relevant parameters. We choose experimentally plausible values for vibrational power dissipation and frequency applied to the lattice as P dissipation is equal to 1 watt, frequency R is equal to 5 megahertz, which gives a final lifetime of a tau minimum 0.003 seconds. We use the same neutron and helium loading values as for magnetic dipole coupling. See equations 84, and the deuterium divided by n is equal to 0.001 multiplied by 0.3 multiplied by 1 divided by 25, and helium 4 divided by n is equal to 0.01, and the same loose correction factor absolute 1 minus n is equal to 0.1 as for magnetic dipole coupling. See equations 83. Evaluating the rate expressions based on the above values using z to the is equal to 2 results in a minimum transfer rate on a screen. Tau minimum on a screen is equal to 3.39 multiplied by 10 to the power of minus 94 1 per second. Since we use the on-screen gamma factor G above, we can consider the effects of the screening by multiplying with the these e to the power of 2 delta G screen, where delta G screen is equal to 49 minus 0.2. Accounts for electron screening of the three channel of the deuterium nuclear wave function, which 350 electron volt screening potential. See section 6.3. The screening factor per section 6.3 comes into twice here since the screening affects the donor side transition as well as the receiver side transitions. This results in a tau minimum screen is equal to 1.84 multiplied by 10 to the power of minus 51 and 1 per second to obtain the maximum rate, peak rate of the decay enhancement pulse. We apply the additional decay enhancement per sections 5.2. Tau maximum is equal to tau minimum multiplied by 1 quarter of n deuterium for n deuterium is equal to 10 to the power of 15. This yields tau maximum screen is equal to 4.6 multiplied by 10 to the power of minus 37 1 per second. Again, this is the population level transfer rate. For example, the rate at which the ensemble in group A transfer excitation to the ensemble in group B to obtain a rate per deuterium pair that is comparable to the estimate given by Koenig and Neuenberg 1989 based on reference 20. We normalize the expressions taking the decay enhanced expressions. We obtain tau maximum screen divided by n deuterium is equal to 4.6 multiplied by 10 to the power minus 52 1 per second, and tau minimum screen divided by n deuterium is equal to 1.84 multiplied by 10 to the power minus 66 1 per second. Similar to the previous subsections, this obtained rate estimate is neither in the observable range nor does it appear to outcompete the spontaneous fusion rate, relativistic coupling in the same physical system as considered in the previous subsections. Nuclei oscillating a different interaction is expected to apply as well. Relativistic coupling results from the fact that oscillating nuclei in the lattice undergo Lorentz transformations, which implies a coupling between center of the mass motion and internal nuclear degrees of freedom. See section 6.7 and reference 93 for more details about this coupling mechanism. For relativistic coupling, the indirect coupling strange between a deuterium helium-4 donor transition assumed to start out in the excited states. For example, as deuterium and deuterium helium-4 result transition assumed to start out in the ground states. For example, as helium-4 is UN relativistic to the power of 2 is equal to phi helium-4 absolute of phi helium-4 multiplied C to the power of 2 pi helium-4 multiplied by pi helium-4 multiplied by phi deuterium absolute of Phi 4, see section 6.15 for the derivation of the terms which yields here given for acoustic phonons. U relativistic to the power of 2 is equal to 0.0362 multiplied by square root nu nuclear divided by nu molar multiplied by e to the power of minus g to the power of 2 c to the power of 2 multiplied by square root m deuterium m helium-4 divided by m. P dissipation tau where the variables are the same as in the prior subsections. Note that the masses deuterium and helium-4 are essentially the same as far as the phonons are concerned. Recall the minimum rates. Starting rate in equation 78, tau minimum is equal to 2 divided by h multiplied by 2 absolute 1 minus n multiplied by v to the power of 2 divided by delta msc to the power of 2 is multiplied by square root n deuterium and helium-4 plugging in un relativistic to the power of 2 for v to the power of 2 yields tau minimum is equal to 4 multiplied by absolute 1 minus n multiplied by 0.0362 multiplied by square root u nu nuclear divided by nu molar multiplied by e to the power of minus g to the power of 2 multiplied by square root m deuterium m helium 4 multiplied by c to the power of 2 divided by delta msc to the power of 2 multiplied by P dissipation tau divided by h multiplied by square root n deuterium n helium 4 divided by n. To evaluate these expressions, we need to consider the values of relevant parameters we take Absolute 1 minus n is equal to zero point 0.1 nuclear divided by nu molar is equal to 6.65 multiplied by 10 to the power of minus 12. G is equal to 90.35, where the volume ratio and gamma factor are for the pH 3 state, and where absolute 1 minus n is the form of the deuterium 3 plus 1 helium 4 contribution to the deuterium helium 4 transition per section 6.5. Moreover, per this section's introduction, and deuterium divided by n is equal to 0.001 multiplied by 0.25 multiplied by 1 divided by 9, and helium 4 divided by n is equal to 0.01, where we assume a loaded lattice where every 1000 units cell contains a deuterium molecule, and where 20% of the deuterium molecules are in the P3 state. See figure 38 in the section 6.1, with only one of the 9 possible P3 states, which J is equal to 1, being involved in the all CP transition. See section 6.9 and 6.8, and where every 100 unit cell contains a helium-4 nucleus, which is experimentally plausible values for vibrational power dissipation and frequency applied to the lattice as P dissipation is equal to 1 watt and a frequency of all is equal to 5 megahertz, which gives a final lifetime tau r is equal to 10 to the power of minus 12 multiplied by 10 to the power of minus 7. If r divided by 1 megahertz to the power of minus 3 divided by 2 seconds is equal to 0.003 seconds. Evaluating the rate expressions based on the above values results in a minimum transfer rate on screen of the tau minimum on screen is equal to 2.32 multiplied by 10 to the power of minus 63 1 per second. Since we use the on-screen gamma factor G above, we can consider the effect of screening by multiplying with section 6.3 the e to the power of 2 the multiplied by delta G screen, when delta G screen is equal to 49.2 accounts for electron screening of the P3 channel of the deuterium nuclear wave function with a 350 electron volt screening potential. See section 6.3. This results in tau minimum screen equal to 1.26 multiplied by 10 to the power minus 20 1 per second. So obtain the maximum rate peak rate of the decay enhancement pulse, we apply the additional decay enhancement per sections 5.2. Tau maximum is equal to tau minimum 1 divided by 4 and duration for n duration is equal to 10 to the power of 15. This yields tau maximum screen is equal to 3.15 multiplied by 10 to the power of minus 6 1 per second. Again, this is the population level transfer rate, for example, at rate at the which ensemble in group A transfer excitation to the ensemble in group B to obtain a rate per neutron pair that is comparable to the estimate given by Koenig and Nuremberg in 1989 in reference 20. We normalize the expressions taking the decay enhancement expression. We obtain tau maximum screen divided by any temperature is equal to 3.15 multiplied by 10 to the power minus 21 1 per second. Such a rate estimate means that this countable excitation transfer would get into the observable range. Let us therefore also consider the minimum rate per deuterium to get a better sense of whether the process of time evolving decay factors from the minimum to the maximum rate has a chance to get started. Tau minimum screen is divided by energy temperature is equal to 1.26 multiplied by 10 to the power minus 35 1 per second. Several points can be noted here. We can see that the estimated transfer rate based on the relativistic coupling is substantially faster than the optimum rates for magnetic and electric dipole coupling. However, these rates are still not in the observable range, while the maximum rate per deuterium pair outcompetes the spontaneous rate from Koenig and Nuremberg 1989 based on the reference 20. The minimum rate per deuterium pair doesn't. Note also that the time evolution of decay factors has to take place within the constraint of the decoherence time of the system. We provide an estimate for the decoherence time in sections 6.21, yielding a value of about 1 nanoseconds. Comparison of coupling strength. The calculations in this section suggest that the maximum rate for cooperatively enhanced resonant excitation transfer based on the relativistics or multiplied by CP interaction is ordered to magnitude larger than what would be expected from the D multiplied by E and micro multiplied by B interactions above. However, all rates estimated in these sections are below the observable range discussed in the introduction, and as can be seen from the equation 75, 76, as well as figure 13, a major hindrance factor is transition through the Coulomb barrier that occurs twice per each transfer, once for the deuterium-deuterium molecule tunneling inward to the helium-4 state and once for the helium-4 nucleus tunneling apart to the deuterium-deuterium state. After this exercise, a faster transfer that we consider to be relevant to experimental reports observable rates will be considered in the next sections. Now I want to go through another chapter 5.4 palladium nuclei as receiver systems. In addition to helium as receiver nuclei, as discussed in earlier sections, heavier lattice nuclei can be considered as candidate receiver systems for the transfer of excitation from the deuterium-deuterium. It is unlikely that such nuclei exhibit excited states precisely resonance with the deuterium-deuterium helium-4 transition at to 23,848,109 electron volt. However, several lower energy transitions can be resonant with the deuterium helium 4 transition, as will be discussed in detail in section 5.7 and the subsequent sections. Comparatively small energy differences can be made up via energy exchange with oscillator modes when the system first starts up. After the system starts up, the receiver system will have more energy, so that states as higher energy than in the vicinity of the multiple deuterium helium 4 transition energy can be accessed, where the density of the nuclear molecules cluster states can be high. As will be discussed in sections 5.10 in more detail, significant energy exchange with optical phonons and plasmons looks to be possible under conditions where the density of states, including states from the multiple transition, is high, and when the phonon mode or plasmon mode, this is the cooled to and emitted into, is highly excited. This section provides an overview of nuclear excited states available in palladium lattice, although most points raised apply to other elements as well. Natural palladium contains six stable isotopes: palladium 102, palladium 104, palladium 105, palladium 106, palladium 108, palladium 110. So excited states from all these isotopes can be expected to be amply available in a palladium lattice when seeking to identify states suitable for nuclear excitation transfer dynamics in mid-size nuclei such as palladium. Two categories of nuclear excited states are candidates that are discussed here. First, there are nuclear bound states. Second, there are nuclear cluster states. We will begin with an overview of nuclear bound states in palladium isotopes and then proceed with an overview of nuclear cluster states with a focus on nuclear molecular states, which represents a comparatively long-lived subset of nuclear cluster states. These sections conclude with discussions of key properties that make candidates excited states suitable as participants in nuclear excitation transfer dynamic. While palladium bond states, you see that figure 15 illustrates and now nuclear bond states for stable palladium isotopes from the nuclear dot database. In the x-axis, we have a different six isotopes of palladium from the 102 until 110, and y-axis we have energy released based on the mega electron volt, and the red lines illustrates proton ionization energy, green lines illustrates alpha ionization energy, and purple lines illustrates neutron ionization energy. Nuclear bond states have been widely studied for many isotopes with aggregated data on corresponding energy level, lifetimes, and transition publicly available in nuclear databases such as Nuclear Dot. Noun-bound states of the stable palladium nucleus on the nuclear data are shown in Figure 15. Above the nuclear ionization threshold in the 7 up to the 10.5 megaelectron-volt range, depending on the palladium isotopes, the bound states are quite unstable against neutron decay. Above the proton ionization threshold in the 7.7 up to the 10.5 megaelectron-volt range, again depending on the isotopes, the bound states become increasingly unstable against proton decay. Similarly, above the alpha ionization threshold and the 2.1 up to 4.4 megaelectron-volt range, depending on the isotopes, the bound states are unstable against alpha decay. Again, the more unstable, the higher above the ionization energy. Proton, neutron, and alpha removal energies are tabulated in section 6.17. The relativistic all-CP interaction is a tensor operated with the magnetic quadrupole selection rules, see section 6.8, and when considering palladium nuclei as receiver systems for nuclear excitation transfer, we are interested in decay-enhanced transitions from the group states of the stable palladium isotopes if the energies, lifetimes, and multipolarities of transitions coupling to the ground states were available for all of the palladium bond states, then we would be able to simply make use of the databases to compile nuclear data with which we could analyze the excitation transfer schemes of interest. However, the datasets of nuclear bond states are not complete. The density of nuclear bond the density of nuclear bond states increase with energy, but the density of the energy levels in the canonical nuclear database such as nuclear dots don't follow this expected relationship. For levels above about 3 megaelectron-volt, this is because at present techniques are lacking to study excited states efficiently and systematically. In addition, there have been no important applications to motivate such studies until now. The nuclear bond states of some isotopes have been studied more comprehensively than is the case with the palladium isotopes. To update, withdraw attention to the bound states of SN120 as reported in the reference 94. An energy level diagram is seen in figure 16. Here we can see that the density of the states increases with energy as expected. This suggests that fewer states are missing from the database. Since the number of nucleus in SN120 nucleus is similar to that in palladium isotopes, we can derive important lessons from the SN120 datasets for palladium nucleus as we laid out below. Figure 16 illustrates non-nuclear bond states for the SN120 teen isotopes, and you see that we have isotopes in SN120 on the x-axis, and in the y-axis we have energy based on the mega electron volt. And purple lines is the neutron ionization energy, red line is the proton ionization energy, green line is the alpha ionization energy. Palladium bound states with M2 transitions to the ground states. Nuclear level diagrams have been developed from the experiments involving radiative decay from the neighboring isotopes, and for experiments involving neutron proton and alpha irradiation. Most of the transitions between the ground states and excited states as a few megaelectron volt or electric quadrupole E2 transitions, which tends to yield large signals in accelerator-based measurements campaigns. There are fewer electric dipole E1 transitions, but these are generally easy to detect as well. The transitions of interest to use involve weaker magnetic quadrupole M2 coupling with the ground states, which tends to be excited less efficiently in collision. Moreover, M2 gamma lines tend to be weaker because electromagnetic quadrupole coupling in radiative decay is relatively weak higher order effect, and as will become clear later on, we are interested in weak M2 transitions, which are in general even easier to miss in an experiment. Consequently, it is likely the case that the transitions that are of particular interest are severely undercounted in the database. So, M2 radiative decay, as will be discussed in more detail in sections 5.8, coherent nuclear dynamics are most efficient in the case of the excited states that are reasonably stable. This is the case because quantum coherence is degraded or lost when an excited state decays. The coherent dynamics are fastest in the case of the transitions that have a strong coupling. However, there is a trade-off. The strength of the coupling relevant to the coherent dynamic is proportional to the square root of the normalized transition strength, O to the power of 2 square root, which can be expressed through a dimensionless coupling constant. V almost is equal to oxygen O, whereas the spontaneous radiative decay rate is proportional to the normalized transitions O2. Tau M2 is almost equal to 2.2 multiplied by 10 to the power of 7 r to the power of 2 divided by 3 epsilon divided by 1 electron volt to the power of 5, or palladium to the power of 2 1 per second, which tau M2 being a Y-scope estimate scaled by the transition range, which we'll discuss further below. For more background on the normal transition range O2, see sections 5.8 and below. Transitions that might be assumed to be particularly suitable for coherent dynamics in the model presented here due to their strong coupling strength are also the transitions which will suffer the fastest radiative loss. This competition between coherent and radiative dynamics and its impact on nuclear excitation transfer at large will be discussed in greater detail in sections 5.8. To estimate how fast this radiative loss might be, we can make use of the Y-scope estimate for the radiative decay. The Y-scope estimate for radiative decay is grounded in the concept of single particle transitions, assuming that the transition matrix elements are primarily determined by the motion of single nuclei. The model incorporates basic assumptions about the nuclear structure, such as the spherical shape of the nucleus and the use of harmonic oscillator wave functions for the nucleus. Catalyst transitions probabilities, but considering the multipolarity of the emitted radiation, for example, electric dipole, quadrupole, and derives standard transition rates for each type of multipole radiation. Bioscope estimates for the radiative decay rate for M2 transitions are shown in Figure 1746. Stable palladium is stored. Later on, we make use of this estimate when determining the minimum excitation transfer rates from the deuterium-deuterium helium-4 transition needed to outpace the coherence processes and to get coherent dynamics into a stable regime. This is in addition to an estimate for the deuterium-deuterium coherence time, which is on the order of 1 nanosecond. Inspections on Figure 17 indicates that even tau M2 transitions are not strong. If fully allowed, the transitions are sufficiently fast so as to impact the coherent dynamics. When the transition energy exceeds 1 megaelectron volt, given that there are very few M2 transitions at or below 1 megaelectron volt. This suggests that we are interested in weak M2 transitions at higher energies. As the name indicates, the Y-scope estimate of the state's lifetime is only an estimate. Actual lifetime depends on the particular dynamics of nucleons in transition, which can go far beyond the comparatively simple considerations underlying the Y-scope estimate. We capture the dynamics that the Y-scope estimate fails to estimate and normalize in a normalized transition state O2 that satisfies a which the respective relativistic coupling and associated transitions or factor can be thought of as the square root of the normalized M2 transition range of the transition. Since our knowledge of how big these transitions must reach elements are in the paradigm is totally limited, we will express matrix elements and rates in terms of the O values so as to explicitly distinguish between transition-specific differences. Consequently, if a transition is particularly weak and its lifetime is underestimated by the Y-scope estimate, its associated O value would be less than the 1. Dataset for E1 transitions in SN120 in Moshe and his colleagues 2022 in reference 94, a list of 249 energy levels are given for SM123, along with estimates for associated electric dipole E1 transition rate. We might expect there to be a similar distribution of levels in transition range for magnetic quadrupole M2 transitions stable palladium isotopes. We use the SN120 dataset in place of the stable palladium isotopes, where we estimated transmission range according to the BAE1 is equal to O2 e to the power of 2 Fm to the power of 2, and also here O2 is almost equal to tau actual divided by tau y scope, and figure 17, which is a decreasing of the line, illustrates estimated lifetimes for fully allowed M2 transitions in the stable palladium isotopes. You see, we have a transition energy based on the mega electron volt in the x-axis from the 1 to the 10, and the y-axis we have a lifetime based on the seconds, and it starts from the 10 to the power of minus 15 to 10 to the power of minus 9, and it's working for 6 isotopes of palladium. The blue lines is for palladium isotopes 102. Orange line is for isotope palladium 104. Green line is for isotope palladium 105. And red line is a palladium isotopes 106, and purple line is for palladium isotopes 108, and brown line is for 110 for palladium isotopes. So thank you so much for watching my tutorial video until the end. Today is the 7th date of July 2026 in the morning. If there is any simulations for this literature that I read about it, you can find it from github.com/maxwell script, github.com slash kashi script, and github.com slash safra script.